applied in functional applications as well as in the structural applications. Velmurugan?
Yes, sir.
If any connectivity problem, just inform, because I could see only the slides here.
Yeah, sure, sir. Sure. I'll inform if there is
Because here there is some issue is going on. So the network.
Okay, sir. Fine.
So if at all
Okay,
anything, see you just.
Fine, sir. I'll make.
Okay. Now that is what the objective of all these designers today. So they want to design new and newer kind of this kind of structures, and they want to reduce the cost, and during the lifetime also they want to increase the functional thing of that. So that means I told only the two objectives, that is the mass reduction and the other one is the energy. In addition to that, any thin wall structure, so they are having one good property called the specific strength. Okay. So now every material, even the conventional engineering materials, are comparing one with the other in terms of the stiffness and the specific strength. Okay. Specific strength is that for that unit volume, how much stiffness it would offer or how much strength. So the specific strength and specific stiffness are very important for any material, new material. So compared to steel, aluminum is having a good specific strength. Okay. And this stiffness is not only a material property, and by engineering your geometry, you can get what? You can increase the stiffness, specific stiffness, you can enhance by the geometry, provision of geometry. Because we know that one simple example is that we know about the steel rod. The steel rod, how much stiff we know, but when they are rotating and fashioned like a spring, then it absorbs the energy, right? It absorbs the shock and energy. So the material property is one aspect. The other one is the geometry. How this geometry is built, so that actually reflect in the stiffness. So this kind of structure, they absorb energy, maximum energy, as well as they are having good stiffness. Okay, they will not get, the dimensional stability is very good for that equivalent mass. For the equivalent, suppose you are producing say 10 kilogram of product with a normal geometry and 10 kilogram of mass, you are designing a product with this kind of structure, then the stiffness will be good. It is having more stiff than your conventional material. So it is having a twin advantage of having good specific strength as well as specific stiffness. So these all to be kept in mind. So first objective is that mass reduction, increase your energy absorption, and you are increasing the specific strength and you are increasing the specific stiffness. Okay, so these are all achieved not with the very high strength material like stainless steel or titanium, though these kind of structures are being built in that the super alloys, but mainly they are making use of this commonly available aluminum material. Okay, we know that they are abundantly available and they have low density. So most of these kind of thin wall structures, they are making use of the polymers, that is composites, polymer reinforced composites or aluminum. Okay, so that is the very advantage of having this kind of thin wall structures. Okay, so now there are three categories of materials in the thin wall structure. One is that your foam kind of things. So if you I think you have some basic idea about that foam. The foams are having kind of a pore structure. They have a porous structures. Okay. How to create that pores? It depends on the material. It varies from material to material. So you can create that kind of foam structure with the steel, and you can create that kind of structure with the polymers or with the aluminum. Okay. So in different manufacturing processes are being applied for producing this kind of structure. So foams are basically, it is having pores, right? The pores are not uniformly distributed, and they are distributed. It is kind of a probability distribution that we cannot say that exactly at this place this much amount of this many pores will be there. So it depends on some other physics. Okay, so there are a lot of research are going on to evenly distribute that pores and all. Okay. So basically these foams are created in two different forms. One is that open cell metal foam and the closed cell metal foam. Open cell metal foams are I think even some of you would have done kind of experimental work on it. Open cell foam we can create in a foundry. Okay, casting we can create, and we can do that in the powder metallurgy also. So we can have some kind of material, so that will evaporate when it is heated during the sintering, and during the compacting, the initial stage where the mechanical bridge is happening. Okay, you are building the mechanical bridge through the powders. There we have this kind of additive kind of things. So when you are heating it up during sintering, it will get evaporated and you are getting the porous structure. And that porous structure is a open cell metal foams. And even in casting also, in foundry, we can get the similar structure. But these are not having much applications, open cell structures. Closed cell structures are, they are produced in mass. The aluminum foams and PVC foams are all, they are manufactured with the closed cell metal foam. So foam is one category. In the thin wall structures, foam is one category. The second one is honeycomb. Okay, they have the second categories. And the other one is our polymer composites. So these three are the class of materials. One class of material, they use the foams. There are n number of foams are now available in the market. You can start from aluminum foam, you can have a steel foam, and you can have any polymer foam, titanium alloy. All these things we are creating foams. Okay, what are the advantages of foam and all? You will see in a couple of minutes. You will see what are its advantages, how to design that, how much energy your designed foam can carry. So those things you will see in a minute. Before that, you will see how these closed cell foams are created. And they created, I told you can create it by ingraining that with the particles. Okay, ingrain that with the, say, for example, you have aluminum alloy face sheets, and you have this metal, aluminum metal there. You embed this kind of ceramic particles in it. Then you can create the foams. Okay, you can create the foams by following these steps. What you can do is by injecting gas into the liquid metal from an external source. Okay, so this gas bubbles will be formed, and that will evaporate as it gets cooled. So that also, when it will entrap. Okay, entrapped gas will escape. Then you will create a kind of foam structure there. By gassing this kind of gas formation in the liquid, by admixing gas released blowing agents with the molten metal, that kind of agents are being put inside this metal, and along with that it will escape from that. Then another method is you can create a precipitation of gas that was previously dissolved in the molten metal. These steps we can create these foams. Okay, so you can see here how this kind of foams are being manufactured. So these are a long aluminum foam structure is created, AFS rolling ingots, and we can even roll it, and these are the big ingots. Then we can reduce the thickness by using hot rolling method. Okay, so you can foam at 580 degrees centigrade, and this is the precursor from that. So with this technique, okay, you can create the mass production of foams can be created using this rolling method. Okay, rolling and foaming is done. Foaming is another kind of process where this kind of blowing of gases through which we are creating these foams. Okay, so these are the manufacturing techniques in which we are creating these foams. Okay. So what are the advantages of these foams compared to the conventionally available metal? So here I have taken this aluminum foam structure. Suppose we take this steel as the baseline. Required thickness for equal stiffness. Okay, for let us say 4.7 mm. Okay, that steel plate of 4.7 mm is taken, and correspond, that is equivalent stiffness we could get in aluminum, and for that we have to design the thickness would be of 6.8 mm. Okay, so when you do that for CFRP, right, carbon fiber reinforced composites, you can see that the thickness has to be increased to 5.6, but you see how much mass is used for steel. Here we know that the density of steel is 7.85, and for aluminum it is 2.7. and CFRP it is further less than that. It is only normally it is 1100 or 1200 kilogram per meter cube. So this aluminum foam structure, normally the maximum percentage of relative density will be only 30%, 28%, 30%. So we are, even aluminum is 2.7, and here we are getting only what? We are getting only 400 and 500 kilogram per meter cube. So that means you just imagine how much weight it will occupy. You see here, with the equivalent mass of steel is 73.3, and the equivalent stiffness we could get using this aluminum foam structure with 12.8 kg. The equivalent for this 8 mm aluminum foam structure is only 12.8. And you see that mass reduction, because it is a baseline, mass reduction you will get around 60 minus 60, but between 83% reduction you are getting in the mass. So I told you, the mass reduction. But again, you look at the cost, because steel, aluminum are all, they are established process. They require less cost for producing that. Whereas if you see that, it is higher than that, but it is not that much high compared to other things. Okay. So that means you are getting aluminum foam structure. It is what? It is only 1,600, 9,600. When you are, suppose today we are getting titanium foams, which are very costly compared to that equivalent titanium alloy. But say aluminums are established process are there. So now they could get around, you see, aluminum conventional material, it takes only 109. That is the cost, in terms of cost, and equivalent in rupees it is 8,200 per kilogram. So it takes only what? It is only 9,600. A marginal increase in the cost. That only marginal increase. But the foams are very costly when you go for some other non-ferrous materials. But the manufacturing processes are being optimized. So once it is optimized like aluminum, then you will get this economic. It would be economic then. So for 1 kilogram of mass of this thing, okay, for every cost per kilogram mass reduction with respect to steel, for every kilogram you are saving what? 68 rupees. Okay, you are saving 68 rupees. And this chart will give you some kind of idea about using this kind of thin structures, okay, lightweight structures. The AFS is superior in terms of even the composites, okay, in terms of its equivalent stiffness, and even in terms of what? Even in terms of cost, this is comparable to that of what? Aluminum. Okay. The next thing is where it is being applied today. So earlier these metallic foams are being used mainly they are applied in this structural materials, okay, structural materials. And today everywhere it is being applied. Okay, today I will take one case studies where this can be applied for a high-speed train. As a front of the train, we can have these buffers, so that it will absorb energy during the collision of train. If anything happens, so it will absorb the energy. So earlier it was applied only for that energy application in terms of this structural materials. So today it is applied everywhere. Wherever you want to reduce the mass or where you want to absorb more amount of shocks and energy, there you can apply this. So you can see some of the applications here. So here it is used in the battery compartment of electric vehicle. So electric vehicle, we know that the mass, the weight of the structure has to be reduced. And for that we are using this compressed aluminum foam structures. Okay, they are being in the seal edges. The module compressing underbody. Okay, underbody, this is the underbody. And battery compartments. This is applied in the battery compartment also. And you can look at this, the second diagram where this exactly being located. You can see crash absorber box. So this is coming at the front of your automobile vehicle where this is applied. It made of a rectangular aluminum alloy profile filled with the aluminum foams. So again, another major application is in the defense sector. All armored vehicle now they are having this kind of structures as the energy absorbing structure, both at the bottom of this vehicles, armored vehicles, that is at the floor, as well as in the front side and in the sideway also can be used, so that it will protect against the occupant against any grenade attack or mine blast kind of things. So these are being applied. Okay, they absorb energy, they absorb shock wave also. They are good at absorbing shock waves. And another application where this is applied, you see here, this is applied in the high-speed train, high-velocity train, and this is, you can look at this. This is applied at the nose, and the requirement of foam is not with the absorbing energy. In fact, this is applied to your absorbing the shock. Okay, you have a huge shock is created when it is going at a high speed of 180, or even today we are high-speed trains. Forget about bullet trains. High-speed trains are now very popular, and even in India it is going to come in another 1 or 2 years. So the speed is normally 180 to 220 kilometers per hour. So at that speed, it has to what? Engage the air velocity and shock. And for that, we are going for this kind of structures. So these structure actually absorb the waves, absorb the shocks. In terms of that, the impedance, okay, they have a acoustic impedance. So they have an acoustic impedance mismatch between that structure. It is actually a layered structure. It is not a one single structure. There will be a layer of material are used, and this layer of material has a different acoustic property called impedance, and through that we could we can in fact disperse the wave. Okay, we can reduce the wave propagation, and through that we are reducing the damage it caused to the structure. Okay, so that also we will see. Okay, so what are the other characteristics of that? It is having low density, we know that. The second one, it is high strength to weight ratio. Second advantage, high surface area to volume ratio. This is like nanomaterials. It's having high surface area to volume ratio. And it is having one of the advantage compared to composites. What is the drawback with the composites? So I hope you can also interact so that it will be somewhat good. Understanding will be good. What is the drawback with all the composites, right? This polymer composites. And in fact, the drawback with the processes like rolling, extrusion and all. So they are good at reducing this. The other things are, the first three are very good. They have low density and high strength to weight ratio. They have good surface area to volume ratio. Everything is good. But when you comes to that fourth property called isotropic load response, okay, this foam will behave like an isotropic material. What do you mean by isotropic? What is the drawback with the other polymer composites? Polymer composites, no, you have these polymer composites. They have a good, even today they are designing with a good fire resistance and all. Okay, in spite of all, they have one drawback. What is the property that is called? Yes? So, Velmurugan, are they interacting or? Yes, I could not get a little louder I can talk so that I'm not using any headphone so that little louder maybe. Yes?
Yes, sir. I think one participant he said something, but voice is not clear, sir.
Velmurugan, my audio is good there, no?
Yes, sir. Your voice is clear, sir.
Okay.
Voice and screen.
So people are they interacting with the faculty members or?
Yes, sir.
Okay.
I think.
So some of you at least interact with me, it would be good, because so these are some basic things which you will teach. Some of the things which you will because all are mechanical engineers, it is told. So it would be good if you interact and I will also get bored. I will not get bored. It will be monotonous because we are in this online this thing. So when I'm at the stage and looking at your faces and all, I could get some feeling of conveying something. Otherwise, this is would not be good. So I expect some of you to interact with me. So I will not pose much challenging thing and all. It's all some basic fundamental ideas only, no. So like I told, no, this you have even manufacturing process like rolling and extrusion, the drawing operations. They have an inherent problem of anisotropic. So when you have anisotropic property, then you won't get expect the same mechanical properties in all direction. Because when it is used as a structural member in the your functional, okay, in some product, then it is expected that the behavior of the material upon the disturbance caused by the external media should be same, irrespective of whether the load is being applied at the x direction, y direction, or z direction. It has to what? It has to respond in a similar behavior. It has to respond similarly. When it is an anisotropic behavior, then what happens? Every direction it will behave differently. So here the advantage of aluminum foam is it is isotropic property. Though it is having lots of pores, and the pores are not distributed aligned in one particular direction, they are in all three directions. What would happen is that we are getting the isotropic property. The stress, of course, compared to the equivalent mass, okay, when you equivalent volume, that stress will be less, okay, strength will be less, but the strength will be everywhere. It is constant everywhere. That is one isotropic property we could get in the foam. And they have a controlled stress strain characteristic. That is also another. So another thing is that it can be heat treated. Okay, it can be heat treated like a conventional material, and they are braceable, can be coated and plated. Then they have effective acoustical absorption. That I told you, know, the shock waves, it can absorb the shock wave, pressure waves, it can absorb effectively. And corrosion behavior is comparable to that of dense aluminum alloy. It is not as good as your aluminum alloy, very good at corrosion resistance, but compared to that, it is good. Now you see the graph where it is of conventional aluminum alloy and the aluminum foam is being compared, and the noise absorption capacity is almost very high. Okay, so this can be applied in the acoustic, okay, the attenuator. Okay, wherever you want to observe the acoustic waves, so we can use this aluminum foam. Okay, so now we'll move on to the second class of material called honeycomb structures. So I told you, we have seen the manufacturing process for foams and what is that advantages compared to the conventional material. Now coming to that honeycomb structures. This honeycomb structures, it is called as honeycomb. Why? The name of that says that it is used by these bees for storing their waxes and bees and all. No, the honeys are being stored to build the kind of structure, the hexagonal structure it creates using the waxes. Okay, it created the wax, and in that it stores the honey. Actually, these are nature created. Okay, these shapes are nature created. Foams are not like that; they are artificially created. But this is nature inspired structures. These honeycomb structures are nature inspired. That too, this hexagonal honeycomb, it's a nature inspired structure. What is so special about this hexagonal structure? Can you tell? Because hexagonal structure has advantage compared to the other different shapes. It may have a triangular shape. You can create square shaped structures. Okay, you can create trapezoid. So many circle also you can create. Compared to all other shapes, what is the advantage of going for hexagon? Why these bees are building this hexagon as the one unit? Any idea? Yes.
Sound absorption will be more.
Yes? It
Sound
can absorb.
absorption will be more, sir.
Shock absorption, okay. Any other point?
Sir, closed packed structures.
Yes?
Black body radiation.
Closely packed structures.
Then? Okay. So these are all good answer only. But the thing is that it has to, the bees have to store maximum amount of honey. So compared to the other, any other shape, if you are, suppose you are filling this with the liquid or something, the capacity of that will be more in hexagon compared to any other structure for that matter. You just populate that with a square or circle or whatever it is. In a unit volume, let's say unit volume. Unit volume, let's say the thickness L and W. So these three are the unit volume. So for any given unit volume, if you populate that with the hexagon and you populate with other kind of shapes, then hexagon will take large amount of capacity will be more. So maximum amount of bees can be stored through minimum amount of wax. That is also very important. You need to spend that bee has to store and has to collect a minimum amount of wax, and within that it can store more amount of honey in it. So this, for a mechanical perspective, in our mechanical point of view, this is having, it absorbs more amount of energy, as one of you told. So it absorbs maximum energy by the virtue of that surface area volume, amount of surface area for any given volume is more. So it absorbs more energy. Okay, it absorbs more energy. So that is the advantage of compared to other things. What are the other shapes are there? You can see here, it's a corrugated shapes. Okay. And other kind of structures are, I told you, the circle you will have, the triangle you will have, and you can have this kind of square shapes, all those things. Another upcoming material hierarchy is this thing. And this architecture, this is called as architecture. And this architecture is called as auxetic architecture. So this auxetic is not a new name. Okay. Auxetic is, it's a popular name. So this auxetic got its name because it behaves differently than the conventional material. So we know about the Poisson ratio. Poisson ratio is what? Lateral strain by longitudinal strain. For any material, this Poisson ratio will be what? What is the Poisson's ratio? Poisson's ratio will be 0.2 to 0.3, right? Your structural materials, steel and all, what we are getting, it is 0.2 to 0.3 like that. So if you have taken for a porous structure, powder metallurgy component, so that Poisson ratio will be close to something 0.5 something, not more than that. It can go up to 0.5. So these are positive Poisson ratio. It is called as PPR, positive Poisson ratio. There are some material with zero Poisson ratio. So what is the behavior of this Poisson ratio is that you take, for example, a kind of tensile sample like this, and you are applying a load, tensile load. What will happen to the length? Length is getting increased. So, and simultaneously, what will happen to the length is getting increased, and what is happening to my diameter? The size of that is reduced. You increase the length, and that is also, its shape is reduced. So that you will get what? Positive Poisson ratio. Unlike that, in the case of this auxetic materials, okay, when you are applying load, when you are applying this kind of things, okay, by the virtue of that, the geometrical arrangement, when you are stitching, what will happen is that this material get expanded. It will get expanded. You'll see in the next slide how it will expand. Okay, so when you are applying load, that is what you are expecting, that your cross section is reducing. Okay, when you are applying load, cross section is reducing, but it is not happening because of the arrangement of the structure, the geometrical arrangement of that. So when you apply load, what will happen? That it elongated, expanded. You see here, this is the original configuration of this. It is called as a double V structure or a re-entry component. Okay, that is nothing but double V structure. You can see it looking like a double V structure. So when you apply load, what will happen? It comes out of it. You can see here the dotted one is what is called as after elongation. When you apply load vertically, what will happen? The final unit cell will be like this. Okay, final unit cell will be like this. Okay, now what I am doing, instead of stretching, I just apply a compressive load. What we are expecting when you are compressing that material, it gets elongated, isn't it? So when you are like a forging, when you are doing upsetting, what will happen? When you apply load, this gets bulging. Okay, diametrical thing will increase, but it is not happening there. When you are applying load, then it further reduces. In the direction of loading, it further reduces. Okay. What is the benefit out of it? So what happened is that when you apply load, the area, effective area against that cross section, right? So that will get increased. So the material is coming to the area of loading. That is where that material is stretched. So in that area, the material from other sides are all concentrated. Okay, so that it increases the strength. The strength of this material is enhanced by means of a structure, the arrangement of this accentic structure. When you are stretching, then it gets stretched. That entire unit cell gets stretched, so that more amount of material is brought to the place where it is being, the force is being applied. So in that way, what we are getting the large amount of energy it will absorb. It will absorb large amount of energy, and the deflection will be, it won't be deflected much. When you are applying a vertical load here, it won't be deflected much. Okay, the stability, the structural stability is retained. So that is axiatic material. And how they are manufactured? The manufacturing of honeycomb cell is simply a sheet metal operation. You have to cut, you have to take the strip like this, and you have to fold this kind of corrugated. Initially, it is all corrugated. They are folded together, and this kind of honeycomb structures are created. Okay, so this is a continuous process. Simple sheet metal fabrication only. These structures are created. The honeycomb structure and other structures are created. You see how this corrugated shape has been created. You can see here. The strip is passing through the V-groove kind of things, and there we are creating this kind of corrugated profiles. And this is example I told you, that axiatic structure, conventional material, when you are pulling, okay, what will happen? It gets elongated. Now, axiatic, when you are pulling, you see the one at the shaded inner one is the original thing. And when you are applying load, what happens? That it is more material is coming in that way. Okay. So this is how it is being structured. Okay, this architecture of the material, geometry is such that when it is pulled, then more amount of material already folded. So the foldings are all unfolded. That is simple. Simple logic is that there are multiple folding happens. When you are stitching, what happens is it is all unfolding. So through this unfolding, what will happen? That more amount of materials are coming in the perpendicular normal to the direction of your loading. That is very important. So here, this is one of the other things, like hierarchical structures. Hierarchical structures are used in shock wave absorptions. Okay. Anyway, we will discuss that when we take that physics point of view. That is called as impedance. So these are graded axiatic cellular structure. You see, this is a continuous material, and initially it is 82% density. So here also it is what? Everywhere it is density only. Okay, here in the honeycomb structure also, how do you calculate the relative density here? For this material, how do you calculate the relative density? Foams, in fact, how do you calculate? Foam density you can calculate by, you can create the Archimedes principle, you can calculate what is that volume, and then you can, you can calculate the mass. In fact, mass is that property you can directly get, and volume you can get from Archimedes. How do you get this here? Theoretically also we can get, you have to just create a unit cell, and we have to find out what is that area of this, total area of that, and what is the area of this sheet metal. Then we can find out the relative density. So normally I told you, foam, aluminum foam, the maximum density is 30%. But real application you will use only 15%, 20% like that. It depends on what is your applications. And here this honeycombs will have maximum density of 10 to 11%. Okay. you will get normally 7%, 8%. The maximum density achieved in honeycomb, that is hexagonal honeycomb, will be around 10 to 11%. Here, this kind of structure, oxidic structure, it will be slightly more. You will get up to 20% also you will get in this oxidic structure. Corrugated structure, we may go up to 15%. Okay, how can you design that? This is what the unit cell for this oxidic structure. So this thickness we can increase. This is the foil thickness. The foil thickness is what? This is your sheet metal. Basically, these are all sheet metal, right? So you can increase the initial sheet metal size so that your total mass of that sheet metal will be more. So you will get better density. Okay, density you can go up to 20 or 30%. Up to 30% you can go for this kind of structures. And corrugated also we can design by increasing the thickness. Okay, you can increase the thickness and get the required relative density. So as you increase the density, what will happen? Your density, as you increase the density, it will absorb the stress. The stress, you can impart more amount of stress there. Okay, then energy absorption will also be good. So up to certain point, okay. Not that meaning that you will increase that to 15%, 16%. Then the thin wall structure concept does not come there. So what we are doing, honeycomb structure, the maximum density we could achieve is 20 to 25%. Okay, foam structure we may go up to 30%. So 20 to 25 for honeycomb structure. Okay, so beyond that, it will not do that energy absorption function. Okay. So where it is being applied honeycomb structure, you can see these honeycomb structures are used in this aircraft structure. You could have seen, and honeycomb structure now you can see everywhere in this, even in four-wheelers and all. No, you could have seen in the wherever they have a plastic components are there. So in order to reduce the weight and increase the stiffness, okay, they are using this. In the bumper, you can see this thing. Wherever you have plastic panels, so they have this kind of structures. And you can see here in the wings, right? In the wings, you could see that this aluminum honeycombs. And honeycombs are now everywhere. Yes.
చాలా టైం పట్టేస్తుంది సార్ ఇది.
Yes. Yeah.
No, sir.
So in electric vehicle is where it is everywhere. Okay, because we know that electric vehicles, it requires lightweight. Simultaneously, you cannot compromise on stiffness. So we are using this kind of honeycomb structures there. So that will absorb energy also. For any collision impact, that will absorb more amount of energy. And another area this is being very prominently being applied is in the armored applications. Okay, here you can see that explosive device, mine blast happens. Then this is what I told you. This is being applied in the floor plate. The floor plate, it will absorb energy, whatever blast waves, it will absorb, and this the waves are being absorbed by the structures, honeycomb structures, and these are applied in the sideway panel also, because the hand grenades are thrown on the it do not happen at the bottom, right? So this is happen when they are using this kind of IEDs, mine blast. So normally they will throw grenades in the sideways. So there also we are reinforcing all these panels with this kind of thin wall structures. So they reduce the weight, simultaneously increase the your energy absorbing capability. Okay. Now coming to this design part of it, how to design a foam, or in fact for that it's same concept applied for the honeycomb also. Design of polymer composite different, but this design of foams and your design of honeycombs are almost the same. Okay, how to do that, I'll tell you. So till the slides, if you have any questions, you may ask before proceeding on to this.
Sir, one small doubt.
Yeah.
Good afternoon, sir. When you're talking about the oxidic material structure,
Yes.
Is that you can able to get the oxidic material only by the change in structure, or we can also get through the alloy also by if you change the compound?
Yes, yeah, you can see material is different. So I told you, all these lightweight thin wall structures, they have a twin objective. One is you can keep on increasing that strength by alloying. We have now this aluminum honeycombs, all these aluminum alloys are being applied. Okay, they are using 60 alloys, 50 alloys being used, 2000 series are used. Whatever new alloys coming up, so having good strength, okay, good corrosion resistance, all these things you can take. It is nothing to do with your material. It is simply because of what? The geometry. Okay, by engineering the geometry, we are getting the property. So negative Poisson ratio in acidic material is not because of what? Not because of the material. It is a geometric property. Okay.
Okay.
So it is, lateral strain by longitudinal strain is what the Poisson's ratio. But whatever our conventional wisdom, our wisdom regarding what? Your conventional material is completely different when you are going for this thin wall structures. Okay, acidic material behavior, you can enhance by properly designing that. Say, for example, here, by changing this angle, normally this is 30-degree angle. Okay, this is a re-entry angle. This is called as a re-entry angle. If you change this angle, then it will reflect, you will get one negative Poisson ratio. So this Poisson ratio, negative Poisson ratio, maybe 0.1, minus 0.1, minus 0.2. This will change as you change the geometric property. These are the dimensions, right? The cell length and cell height, okay, and this thickness. What? Influencing your negative Poisson ratio. You will get different Poisson ratio, negative Poisson ratio by varying this. And it is not, of course, depend on your what? It is not depending on material. Okay.
Thanks.
So for aluminum, one particular alloy alone, maybe you are taking 50 series. And that 50 series itself, by varying this combination, you will get different Poisson ratio. And that will change the energy absorption behavior completely. As this negative Poisson ratio more and more, the energy absorbing capacity will be more. For a given material and for a given mass and given relative density, when you could achieve large negative Poisson ratio, that energy absorption behavior will be good. Okay, these are all the design aspects.
Thank you, sir. Thank you.
So now coming to that, how to design. Okay, we'll see. This is the normal stress strain curve, and of course we know about this stress strain curve for what? Stress strain curve for your engineering materials. So they have this elastic limit, then you will have yield point, then your flow localization or instability point, and this ultimate tensile and all those things. So now it's different for this kind of material. This foam and other honeycomb structures, mostly they follow like this. Okay, they follow like this. You could see three distinct regions here. One region is that elastic region, that is straight. The slope is one single slope will be there. Okay, this is a straight one. And second one is that is called as a plateau region. The plateau region is what is called as, it is where actually you can see the slope is very gradual, almost constant here. Sometimes we could get a very horizontal thing. That is for a same stress, load, same load, as long as you keep applying the load, the strain will happen continuously. Then this third one is the densification region. Okay, so once the densification starts, then it starts performing like a 100% dense material. Now we know that they have actually they have not fully dense. They have 20% or 30% density compared to that conventional material. So what is in the first region happens? First region, if it is a foam or even honeycomb structure, so they will not closing down. Crushing will not start. Okay, crushing will not start. So at the end of this first slope, the crushing starts. When crushing starts, what happens? That the height is decreasing. Initially height may be 30 millimeter or 40 millimeter. Okay, so when you apply load, what happens? This is getting reduced. Okay, so this is the because of the crushing. When it is increasing, no, it means what? The strain hardening is very low here. So the curve, that is your normal engineering material, the curve is going in this fashion. So that denotes what? Your strain hardening is increasing there. So that for increasing your strain, you have to apply more load. That means stress required will be more and more as you want to increase the deformation. Here, it will happen at the same load or a very small amount of load is required for further deformation. That is because we just have to crush this and there is no strain hardening effect happens. So everything is now closed. Say for example, in a foam, after some distance, okay, you are completely crushed it. Okay, it is getting 100% dense. You see here, this is where 100% dense happens. That means it is started performing like what? Started performing like a conventional material. So, from first region, stage 1, small bending and things happens. Small bending and stretching happens, but it is not reducing its height. So, onset of plasticity in buckling or pressing is started here. So, from there it is called as plateau region, and then at the end of this region, your material is completely compressed and it started behaving like a conventional material. Okay, so there are 3 distinct regions. Now, which region is we are going to utilize? We are going to utilize this region. Okay, this shaded region is what we are going to utilize. So, the amount of energy we know. What is that amount of energy here? How do you calculate the amount of energy? In this case, normally we know that for engineering materials, we know what is this. How do you calculate the energy? There are 2 types of energy, right? You have elastic energy and you have plastic energy. How do you calculate that? You are using what? You are using 1/2 of sigma into f naught bar. Okay, you are using that. That you are using for you are using like okay, energy absorption will be. So energy absorption will be what? Your 1/2, and what you have to do, you have to integrate what? Sigma df naught. So this is what your this thing. So this is strain path, 1 by. So this is happen for both your elastic energy and plastic energy absorbed. So here for this foam or this honeycomb, this is called as energy absorption or specific energy absorption, ACA. So that ACA is not 1/2. It is simply, what is that? The plateau region. Okay, what is that stress at this point? Plateau stress. Okay, you got this plateau stress. So you got this plateau stress multiplied by what is the densification? How long this deformation continues from here to this point? Okay, this point. So that is your densification strain. That is your densification strain. Now you see, this is specific energy absorption capacity. Okay, so now look at this diagram I have given here. So 3 material I have given here. The stress versus strain for 3 different materials, each with a different density. The first one, red one, is that 1.92 grams per centimeter cube. We know that it is 2.7 is the gram per centimeter cube is for the aluminum. So it is almost how much it will be, around 60 to 65% density. Now see that the next one is further increase. The density is larger here. It is 2 grams per centimeter cube. So what is the behavior of this stress strain curve? As you increase the density, it goes up and up. That means your plateau stress is more. Plateau stress is here. You can calculate the plateau stress. And if you want to find out the energy absorption, this is energy absorption for the lower density, and this is the energy absorption for that higher density, like this. So it goes higher and higher. That means energy absorption capacity will be more. Okay. But other thing is that when you are going higher and higher, only up to certain limit, then it behaves like the foam structure. That means energy absorption happens. So when your density is more and more, what happened to your this thing, F naught D? Can you tell what will happen to F naught D? As the density is increasing, your curve is, if you I think you have this idea about this when it is closed. Now it will be very apparent in here. So this is where this is where the closing happens. So when you increase the density, it is happening here. When it is happening here now. So when this somewhere, as you increase the density, the densification strain is what? It is reduced. But your plateau stress is more and more. Okay, plateau stress is more and more, but the densification strain is less. Because of what? The amount of crushing distance will be less. as you increase the density. But you will get slightly higher energy absorption for a higher density material. But this behavior is keep reducing, and you cannot use this material for energy absorption after certain. If it is less than 0.5, it is not of use. The strain has to give at least of 50% of the 0.5 will be the true strain. Beyond that, it will not be very much effective. So it depends on material to material, change from material to material. So as you increase the density, your densification strain is less, and because your plateau stress is more, it is getting more, and this is getting less. So your specific energy absorption will not be varying much when you are increasing the density. So as you keep increasing the density, what will happen? As you keep increasing the density, what is the disadvantage with that? I told you now that you have to keep it in mind, that one, mass reduction and energy absorption. You won't get much increase in the energy absorption, but your mass is getting increased. So that is not advisable. So we have to keep this relative density as minimum as possible, so that the energy absorption should also be more, and the mass also to be optimal. So is it clear? So this is as a function of density. The next one is that when you increase this velocity, what do you mean by this velocity? So this kind of materials being applied in a moving vehicle, like a car or some automobile. And basic idea is that it has to absorb the shocking, it has to absorb the energy during the impact or collision. So that is normally will change with respect to velocity, because we know that the stress strain curve will vary with respect to strain rate. And of course, that velocity is a function, the strain rate is a function of what? The velocity of the object that is impacted on it. So as it increases, you can see here, so as it increases, and this gets more and more, you see the last 100 meters per second, and you are getting, this is the curve for them. And there is no much variation in it. There is no much variation in it. Compared to that, the steady state application of load, the impact load does not cause much variation. So finally, it is reported or concluded that you can design this energy absorption and design this dimensions simply using what? The steady state sustain values. Okay, you can calculate the energy absorption using the simple sustain curve taken at the quasi-static condition or at the steady state condition. So that is applicable even if it is to be applied, or application is at the impact load. So where it may go up to 100 meters per second. In that load also, the energy absorption will be almost the same. Okay, maybe the closing of the crushing, the time required for crushing will be less, as the impact speed is more, but the amount of energy consumption will be what? It is more or less same. That is what we could get from this graph. Okay, so this is for almost, as I told, so this honeycomb structure also, so they have behaved like this. Okay, they have behaved like this. As you increase the density, you can see that this is going in this way. Again, like this foams, they have a three distinct pattern here. One is that, so here the elastic behavior will not be so much apparent, whereas this is the plateau region kind of things, stage 2. Stage 3 is the densification region. So it is not, the first region is not apparent there, but this allowing a two distinct region. One is that the closing region or compacting, this is a fully compacted region, and this is where actually the load is getting applied on it, and the height is reduced. Okay, height is reduced. So these are the curves for force and deflection, and see how this midpoint deflection happens in a normal load, how it is applied, you can see. And this actually the property of that is tested in different directions. You have three directions I told you, and they are not behaving like an isotropic material like foams. So they have anisotropic particle. Okay, this thing are anisotropic material. So that means they have orthotropic. They are behaving like a orthotropic material. What do you mean by orthotropic material? Anisotropic we know. What do you mean by orthotropic? Because you would have heard about this, composites. The composites are orthotropic material. Means what? What do you mean by orthotropic? So as far as these honeycombs are concerned, so they have different. One is that this is what no, this is the thickness direction, and this is the length direction, and other one is that width direction. And if you see the property of this material, in this three mutually perpendicular direction will not be same. So for that, what we are doing, we are conducting this tensile test on all three directions. So that is, we are getting three Young's modulus there. We are getting three Young's modulus like E11, E22. Okay, three Young's modulus we will get. And similarly, like composite materials, you will get three shear modulus. Okay, you will get 1, 2, and you are getting G13 and G23. And these are in plane load, in plane stresses. Okay, these are nothing but in plane stresses. 1, 2, 1, 3 are shear loads. 1, 2 direction or in 1, 3 direction or in the 2, 3 direction. Okay, so the properties of this kind of structures are fully we can analyze or we can use for design if only you know all the 6 elastic modulus. Okay, 3 elastic Young's modulus and 3 shear modulus. Okay, so this is something similar to your orthotropic material. Ortho means what? It is 90 degree. Okay, so we are conducting the test for 0 degree, 90 degree, and 270 degree. Okay, on in the 3 direction we are getting this resistance. You can see the behavior of that. You can see here the longitudinal strain versus Poisson ratio in the 3 directions. So that is the first one is the triangular one is that for the y direction, and x direction you can see the Poisson ratio is in the negative thing. And this is what I told you know, this axitic material. So this axitic material, so this is, they are having different Poisson ratio as a function of longitudinal strain. And you can see that the comparison of the trusses means a simple stress like this arrangement. It is not a honeycomb type of thing. Conventional honeycomb is this thing, hexagonal honeycomb. And this is what I told you know, the re-entrant honeycomb or axitic structure. And see the sustain curve here. The re-entrant honeycomb, you see the deflection, maximum deflection you are getting what? You are getting more than 15. Okay, for same, these are conducted for same density. That is the mass of the material remains same. And this re-entrant axitic material, so their deflection and the elongation is very good compared to your conventional honeycomb and the truss material. Okay. Yeah, this is what regarding this honeycomb and foams. If you have any question, you may ask. So this is the basics for designing the material. Okay. So for your application, you are told that this is the energy, this much amount of energy has to be absorbed, and this is the space limitation. Then we have to suitably design the material. There are manufacturer catalogs are there, hundreds of different honeycomb sizes and shapes are available. So we can select one depending upon our applications. So for that we have to initially design this much amount of energy I should absorb. Okay, so for that this should be the stress and this should be the strain, and for this is the units dimensions for that. What should be the size of that honeycomb cell, or if it is eccentric, what is that angle of that re-entrant angle, and what is the thickness of the foil, and other things you have to design. Okay, so some other design aspect here. These are some material data. Okay, I told you that the density starts from 10 to 104 kilogram per meter cube. The density is so small for that. Density is very less. And see the energy absorbing capacity for these materials of different. So one is that you can, these are the density available, and in the graph also you can see for different density for from 26% till 46%. This is nothing but relative density. Rho star is nothing but the the density of the actual density of the foam and divided by what? This is what the density of the fully dense material, solid material. So 0.263 means 26%. So on the vertical axis, it is energy absorption capacity, watts per millijoules meter cube. Watts per millijoules, right? So that is what it is mentioned here. Energy absorption capacity, millijoules, I think it's W, it's not W, in fact, W and millijoules per meter cube. That means if you are selecting, say for example, I take one from how to use this graph, I'll tell you. Say for example, I'm using this first material. What is the first material? First material is density is 26.3. Now for these, the strain, maximum strain, it can go up to 0.7 something. And now how much maximum capacity I can go up to is this one, something here. Okay, this is something close to 5 megajoules. Okay, this is megajoules per meter cube. The unit for that is megajoules per meter cube. That is meter power -3 they have quoted. So it is megajoules per meter cube. Now this is what? It is 5. Let us assume this is 5. What is the meaning of this? If you are using a honeycomb of this density for 1 meter by 1 meter by 1 meter, how much energy it can absorb? 5 megajoules. It can absorb 5 megajoules. So you have to get the volume in terms of meter cube. You just multiply this with the 5. Suppose you are using 1 meter cube, such a big shape material you are going to use, structure you are going to create, then that can absorb an energy of 5 megajoules. Okay. Suppose you are using 0.1 meter cube, then it can absorb what? It can absorb 0.5 megajoule or 500 kilojoules. It can absorb. Okay. So this is the compressive stress. How much compressive stress it can subjected to. So that also you can see from this graph. Same thing you have to do. So like this, literature available for different kind of material. So this is for a kind of aluminum material. Okay, so for this is for aluminum, A0, A6061 and other alloys. Okay, this is for aluminum alloy only. So for different density, how much energy it can absorb and how much stress it can be induced. So that you can get from this. So a lot of papers are available and you can start with your work something and you can go for applying for some of your product and you can test it for your applications. Okay, so up to this point, any because these are the fundamentals I want to teach you. Then we are going slightly the higher ideas and topics. So in this thin wall structure, I told you this how these shock waves are observed and how the stress wave propagation can be minimized using this kind of structures. You will see. So if you have any question, you may ask. Yes. Anything regarding this design aspects or in the previous curves and all? Any questions are there? So what we have seen is that I told you that many different kind of structures and what is that and sustained behavior, how to calculate the energy absorbed from that, how to use that standard literature files for designing our own products. That's what we have seen. Now we'll move on to how this stress wave can be mitigated. Shock mitigation. Shock mitigation means something like, so reduction or absorption. You stop this the shocks propagating or moving in the direction of waves. You will see. Okay, so these are based on one of the physics concept called impedance. Okay, shock wave impedance. So this shock wave impedance is a very important concept for designing this material. Okay, now we know. So you can have your own structure. So you can have this metallic foam you can create. You can you can take one layer as honeycomb, one layer you can use that foam, combination of this layer, or even foam of that. One we know that they have a good energy absorption capacity. The other one is that how they can mitigate the shock. Okay, shock wave can be minimized. That's what we are going to see. And we will take, for example, this kind of structure, a pressure bar, where we have a different kind of materials at different locations. Maybe you are using a titanium or stainless steel, after some distance stainless steel, aluminum, like that, so many materials you can use. And if one of the part is induced or impinged upon some shock, or you are applying some impact on one material, so it is transferred from one material to other material. Okay, you are getting, so for example, you have like this. Yeah. For example, let us take like this. So here, this is something, it is no channel you are creating, then you are inside that, you have so many materials, they are arranged in order. So you have steel, you have brass, aluminum, you have something, composites you have, okay. So here I am applying some shock wave, okay. So you are applying some shock wave, or it may be a mechanical load also. Here I apply that light gas pressure, and that this is a striker bar, and this striker bar and come and strike here, and it creates what? It applies load, it creates a stress. That stress is passing in this way. Okay, it is going in this direction. It is going like this. Okay, now there are some junction in it. Okay, this is one junction between steel and brass, and another thing is that brass and aluminum. Then aluminum and this something other polymer composite is there. So like that it is there, every junction. So what we are thinking is that the stress that is generated as it moves from this steel junction to the brass, once it crosses the interface, what we are assuming that there will be no stress in this region, isn't it? The steel is not free, it is freed from any wave, stress wave. And the entire wave is now moving towards brass, then to the aluminum, then to the polymer composite, like that. But it is not so happen. It is happening like some of the material, that the wave, the stress wave is reflected back to the steel. Okay. There is some incident pressure is acting on that. Then some pressure is reflected, something is transmitted. And from brass to aluminum again, some amount, some percentage of that incident pressure is transmitted and some amount will be absorbed. And this keep going like this. Is it understood? Okay, so initial thought, what we are thinking that once it crosses that and enter into that other material, stress waves, okay, stress waves, then we are assuming that it is completely relieved from any shocks, but it is not happening. Something is reflected back. So something that something reflected back depends on, okay, that depends on the property called impedance. Okay, that impedance decides how much has to be reflected and how much has to be transmitted. So based on some basic physics formula, we are going to get it. Okay. Now let us assume it is having in one particular structure, and this is a stress generated here at a distance of dx. It is created. It's a simple slab analysis we are practicing in this mechanics. Okay, so now we are calculating this differential force there, and that is the relation for the differential force. We can get A dou square U by dou x square. Simple ordinary differential equations. Okay, ordinary differential equation. Then the same dou F we can write in terms of the second law of motion, second law of Newton's second law, mass into acceleration, like this. Rho A into dou square U by dou t square. Okay, so now in this case we can compare these two relations. One based on the simple stress strain relationship, the other one based on the second law of motion. So now we can compare these two, and we are introducing this parameter called C. that C is nothing but what? The elastic wave. It is an elastic wave. When a stress wave is generated and this elastic wave is transmitting and it is going to other materials till it stopped, and the speed of that elastic wave will be like this. Okay. As long as this is within this elastic regime. When it is crossing this elastic regime to plastic regime, then this will be different. Okay, this elastic wave is now square root of E by rho. C equal to E by rho. Now what we are doing is that we are writing a representation of this, the displacement. The displacement of wave function, we can write this like this. F of x minus ct g into this is the positive direction is where it is moving the direction of wave, and this is in the reflected one. This is the transmitted one and it is the reflected. So now we are writing this displacement, that is displacement of wave motion. This is the wave motion, wave displacement as a function of what? Time and the your C value. That is the C value is the elastic wave. Then we know that this strain is what? Du by dx, and we can write like this. Then finally the stress can be related with that. You are getting this relationship. Okay. So now the stress equal to E into epsilon naught. We can rewrite that equation as something like that. And that is equal to what? E rho C. Okay. E rho C. Or we know that C is nothing but square root of E by rho. And then we can write this sigma as a rho C. So I explain it again that the displacement, the representation of displacement can be defined in this way, in a wave form. Okay, where the C is what? Your C is the velocity, that is elastic wave velocity, and T is the time at any time, any point in time. Okay, so we can calculate this strain from that, and we are getting this stress from this. And stress we are taking only the positive wave, that is the direction of, we are taking the wave which is passing in the direction of the movement. The striker direction is this one. We are not considering the reflected wave. How much is transmitted, the direction of impingement of your stress. So that we are calculating. Then this sigma equal to rho Cv. And this rho into C is what is called as the impedance. Okay, rho into C is what is called as impedance. Right? That Z value is something called as impedance. So this impedance is now an elastic property, and this mainly for the stress wave transmission. Okay, now coming to that, the transmitted wave, this is the basic things that, the physics thing, that the force, F is force, and the transmitted force will be equal to what is that force applied on that and what is the force reflected. So the sum of these two will be equal to your transmitted force. So Fi plus Fr equal to F. Or in terms of velocity also we can write in terms of this. And now this is imposed. This one is the condition for how much amount of the transmitted wave. Okay, what is the stress transmitted is sigma T, and what is that transmitted, what is reflected back is sigma R. So that depends on these two factors. That is, sigma is the instant stress. Suppose you are applying that impact load this much, we can calculate the sigma R from sigma I from that. Sigma I is nothing but what? The instant stress. The instant stress is sigma I. And T1 and R1 are some ratios that we are going to find out. This is the T1 is the transmissibility factor and R1 is the reflectivity factor. So T1 is nothing but 2Z2 divided by Z1 plus Z2, and R1 is Z2 by Z2 minus Z1 divided by Z1 plus Z2. Okay. So that means you see here, this is the first material where we are applying this load. So sigma I is here. Then this is instant stress. And this is the second one. Now we can calculate the Z1 and Z2. Z1 is what? The impedance for the first material. And Z2 is the impedance for the second material. Now what are its things? Rho 1 is the density of the material. C we know that E by rho, square root of E by rho. So Young's modulus of the material and this density are the factors to be considered for impedance. So for these kind of things, if you are designing different layers, you can calculate the impedance for each and every layer. Then now apply this principle. You see here, the first thing and second thing, Z1 and Z2 is known. You just understand this T1 and R1. The reflected is what R1 is Z2 minus Z1 divided by Z1 plus Z2. When Z2 value is or there is a huge difference happens between, that is E2 is larger than E1. That means what? That means what? It will be reflected. Okay, Z2 minus Z1 means what? Large amount of things will be reflected back. And transmitting, no, when Z2 what? This is Z2 is the 1 minute. So you see the transmissibility. Z2 is what? The impedance of the second one. When this value is large amount of stress will be transmitted. So what we are expecting is that the Z2 should be as small as possible, so that the T1 value will be what? It is less. When it is small, then this value will be less. Then your transmitted stress will be very less. The amount of stress transmitted to the next structure, next level will be less. And the reflection, what happened? When Z1 is large, Z2 is small, means it is negative. R1 is negative. It is going back. It is going back. R1 will be going back. So this is called as the impedance mismatch. Okay, impedance mismatch. When this impedance mismatch is larger, then what happened? Then suppose if it is induced with the some incident, say 500 megapascal. 500 megapascal is induced on that. So only 100 megapascal is transmitted to the next structure, and 400 megapascal is what? It is reflected back. So everywhere, from one structure to the other, how much will be transmitted and how much will be reflected, you can calculate. Say for example here, so this much amount of energy is transmitted to the next one. It is going gradually like this. And from here, when it goes to the second layer, what happened? This much amount is transmitted and this much amount is reflected. Okay, you see that the backward arrowhead are all they're reflected. You see then when it goes to the next, the first one is the black in color. So both reflected and the transmission in the black in color. To the second layer, it is green in color. That means they are transmitted to them. Then at this interface again, some of that is transmitted, reflected back. Okay, reflected back. That is green backward coming. Then it goes to the next level. The third level, the stress may be further decreased. So it is going in this way, red color. And this red color is reflected, and that the same thing is going to the first also. You see, it is continuously in action. It is continuously in action. That the reflected wave from the second material or third material, it is reflected back here and reflected till this first point, first layer. Okay, like this, it propagates and goes to the boundary or the support structure where it is very minimal. Suppose if you are using a shock wave of 1000 megapascal here, and it will be very minimal here, 50 megapascal, or even we can reduce it to almost 0 L. So this is why we applied in the wherever you know that this is subjected to shock wave applications. Okay, so shock wave application is happening in the high speed train or even the blast structures and all. We are applying this kind of materials and this kind of things. Okay, so have you got this point? So here, for designing this thing, what you should know, suppose for example you are using this lightweight structure. I'm going to use that first as that foam, second one is that axiatic structure, the third one is something I'm going to use honeycomb. Okay, so as I told you, the impedance is a function of what? The function of what? The density and the Young's modulus. So the Young's modulus and density will change from one material to other material. Okay, it depends on the mass property. So what happens? You can design the structure in such a way that impedance mismatch is gradually decreasing. Okay, so that you will get the stress wave is dispersed. Okay, dispersed, and the stress propagation to the next structure can be minimized. So this is a very important concept in the design of layers. Okay, if you are designing a layer of materials, Okay, any structure. It is a structural material. It may be a automobile or any moving vehicle, or it may be something structure. And for that, to avoid the shock wave, we can adopt this strategy. You have any question, you may ask. Do you understand the concept? Yes.
Sir, yes, sir. I have one doubt.
Yeah.
Sir, how to calculate displacement value of transmission and reflections waves?
How to calculate?
Displacement value.
This one you are telling?
Sir, next
Displacement
one,
value
sir.
or what you are telling?
Sir, displacement values.
What you are telling, how to calculate the displacement, right? Deflection.
Yes, sir. Yes, sir. Deflection.
That is no. So here, that is fundamental. Your structural principle will not change. So, for example, you have a structure like this. I have a structure like this. Maybe diamonds, maybe your cross section will be like this. No, you have a square cross section, and this is what the stress. This much amount of stress is incident upon that. Now, can't you calculate what is that strain here? You know the Young's modulus of that, right? You know the Young's modulus. And from that you can calculate the strain. Am I correct or not? That is not change. That will not change. Say for example, there are how many layers are here?
Sir, 4.
Huh? So this is a striker bar and this hit here, and you have 4 material, right? One
Yes, sir.
material, 2, 3, and 4.
3 and polymer based material.
What I'm telling, so here with some velocity something is hitting or some
Okay,
shock wave happens.
Okay,
Assume that is 500 megapascal or something. How much this material will be strained now? The first material. It depends on how much strain will happen. It depends on the Young's modulus. Is it or not?
Yes. Yes, sir.
Yeah, this is, you know the stress and you know the Young's modulus of that. Then you can calculate the strain. Then this, you know the original length of that. You can calculate the displacement from that. That
Okay.
will not change. Now, the question is, how much will be transferred to the next layer? How much transferred to the next layer? That depends on what? Impedance mismatch. Because two materials are come into contact. So the junction, what we are expecting that the same 500 megapascal is moving to the next structure. It is not happening. It is not happening like that. So only a part of that is moving to that. So how much will be transmitted? How much will be dispersed? That depends on what? These properties, right? Z value. How much? That depends on the Z value. So you have to engineer, you have to properly design the structure in such a way that you can explore or exploit this thing. We have an impedance mismatch which reduces the shock wave. Okay, so that we can do. 500, you have only 300 is passing to the next level. Then what happened? Again, you know the Young's modulus of that material. Say for example, this is first material is steel. You know brass Young's modulus. Now the deformation for that material is, you can calculate if you know the Young's modulus and the stress induced there. Then part of that stress is induced to the aluminium. Here you can calculate what is that Young's modulus and the density of that. Okay, so you can calculate the impedance and you calculate what is the stress induced there. Then calculate the displacement. Like that, theoretically you can calculate how much how much it would be displaced. That's what your question, right?
Yes, sir. Thank you, sir.
So that is that is nothing to do with this impedance. That is normal engineering material principle, structural material principle.
Okay, sir. Thank you, sir.
Okay. So now you see here that how, say for example, this continuous impedance graded material. Continuous impedance graded material. That means I think one of the session is functionally gradient material. When you are continuously graded, say for example, density is keep on increasing. Right? You are increasing that density or you are increasing the Young's modulus of that. So that means what? You are continuously as a function of distance, you are having different density and different Young's modulus. Then what happened? Then this stress is gradually reducing like this. You can see here, it is gradually reducing like this. So initially here it is very hard, then it is slow down here. When it is coming to that last one, this is where the projectile is coming to. So like I told you, this hand grenades and all. So when you are using this kind of material, this hand grenade at the initial impact, this will be very hard. So because of the impedance, the stress wave propagates will be less and lesser, then becomes completely the stress wave propagation is stopped at one location. Okay, so right. So another half an hour, I will take two cases where this can be applied. So one is that the honeycomb structures used in the high-speed train. So this paper was published in a Crashworthiness journal, and here they are applying this honeycomb structure at the front, and they have implemented this also in the high-speed train. So they use the two buffers on two ends, and in the high-speed train, this is called as a head car. Okay, it is called as a head car, and this is the middle car. Head car, middle car. The middle car is where the compartments are there. Okay, then this is called as on both sides the head cars are there. Actually, when you want to change the direction, then automatically what happens? Then you will turn it and you will use it. This is the middle car of it. So the energy absorbed by the impacted end of an head car, they are using this kind of principle, and these are the convention. Different designers will use different factors. R1 is a factor, okay, and FD is R1 is a factor, and FD is another dynamic factor. K1 is the energy that is being absorbed. So now K1 is nothing but what is the mass of the total mass of that vehicle, that is train, and what is the velocity. Normally the velocity may be 250 km per hour and all. So we can calculate this much amount of energy has to be absorbed. So this is applicable for even a small vehicle. You are designing for say two-wheeler or even for some car. So there we are calculating this, and we are analyzing. We can find out the energy absorbed by the impacted end of a car. Then how much will be transferred to the middle car? So this is the middle car. This is the head car, and this is the head car, and this is the middle car. A fraction of that is passing through this. So that is also another factor is used, R3, and we are calculating this energy impacted on the middle car, front end of the middle car. Then we are in that paper, they have identified that these three are for three different speeds. Okay, not at very high speeds. The mass they have used as 84 tons. Three different velocities are considered here, and for that the kinetic energy absorbed by the head car is this much. And now applying a factor, we could say that safely that this much amount of energy is absorbed by the front end of the middle car. Okay, front end of the middle car. That means here in this section, front end of the middle car. Okay, for that, this kind of layered arrangement is happening. One is they use that honeycomb structure and thin-walled structures. A thin-walled structure is this thing. And small beams are given, this one, the outer casing like this. So this is a thin-walled structure, and this is your honeycomb structure. You see here, the direction of this is the thickness direction of honeycomb. This is given in the direction of your impact. And here you see this is the direction of impact. So these are aligned in this way. Suppose if you want to safeguard your vehicle at the floor plate like this, so then the honeycomb arrangement should be thickness direction should be in this way. So what is that shock wave or what is that impact direction? And in the direction of that impact, that has to be designed. Okay, now there are three different structures are designed. One is that normal simple casing, and the second one is that thin-walled structure. I think I have not copied it properly. So they have something like here, one single corrugation, and here they use two corrugations, one single corrugation and two corrugation they used. Okay, so they want to compare this one numerically. Okay, so numerically they want to compare, and they compare the established theoretical values. Okay, so the first thing is that they have used this kind of layered arrangement, thin wall structure and this honeycomb structure. So honeycomb structure is the aluminum one, and this they have used that steel. Okay, the casing is the thin wall structure is the steel. And the next thing is that for doing this analysis, we need to know what is the dynamic property of this, that entire structure. Okay, entire structure, what is the dynamic property? So the different strain rate has to be done. This is what the dynamic testing. Okay, this is the dynamic testing. And if you see that stress strain curve, not much difference happens as far as the maximum stress is concerned, but the maximum strain, maximum deformation achieved may be different. Here it is maybe 0.5, and for one particular thing, higher speed, it is, see for example here, strain rate for 3180, which is maximum, and for that it goes up to maximum of 0.5, maximum of 0.5. The red one is that, it is strain rate of 1021, and this, the black one are nothing but they are having very smaller strain rates. It's smaller, that means e to the power of 10 to the power of -5 per second. This is strain rate values, and for that they use this stress strain curve, because this has to be used in the analysis to calculate what is the deflection and what is that energy absorption and all. We have to do the analysis. For that, this stress strain rate behavior is very important. Then these are again property for thin wall structure. Thin wall structure means that the outer structure alone, not this honeycomb structure, thin walled structure. So for that it is thin wall structure. This is the density and Poisson ratio, Young's modulus, some other properties like beta, and this is the yield stress, the Young's modulus, tangent Young's modulus, and some other factors. Okay, this is also calculated. Then I told you, this honeycomb structure having an orthotropic property, and for that we need the elastic constants. All the 6 elastic constants are required. This is what elastic constants, Young's modulus elastic constant, and the shear modulus elastic constants. In addition to that, what are the things required? This is for the fully compacted material, and this is for the fully dense aluminum material. What is the shear modulus? And this is the Poisson ratio, and we know this is the yield stress, and this is the density of that. You can see here the H1 is now different honeycomb structures are used. Okay, so how to vary that structure? You have to vary the cell size. I told by increasing the thickness or by increasing the length, by reducing the length, either by increasing the thickness, that is seat thickness, or reducing that L. What will happen when you are reducing the L? So many cells will be there in the unit area. That means your density will be more. Okay, your density will be more if you are reducing this length. So per unit area, you will have large number of small honeycombs are there. Small hexagons. How many hexagons are there? When you are reducing the size, so many hexagons are there. That means the mass will be increasing or density will be increasing. So 3 densities are being tried here. Okay, so these are the we can theoretically calculate. I told so to calculate this sustained behavior in 3 directions, orthotropic direction, you may do the tensile test like this. We can conduct the tensile test in all 3 directions. Okay, in all 3 directions we may conduct the tensile test, and we can get this these properties like E11, 22, 33, shear modulus 11, 12, 23. You can calculate. Or we can go for theoretical method. You can calculate theoretically also. You can do that. So this is the compressive strain for that 3 things. H1 is for the lower density. H1 is that lower density, which is H1. Here it is 3184, or the density is 93.531. Where this the thickness remains same. All those things, that seat thickness is constant, but we are varying the sizes. Okay. Here it is for unit area, the number of cells are less, and here it is more, 187. So what will happen when you increase that cell size? You see here, when you increase the cell size or density, what will happen? That sigma d value will be, your plateau stress will be more. This is what the plateau stress we have seen in the previous slide. The plateau stress will be more, and your densification, there won't be much change in the densification here. There is not much change. So energy absorption will be more as you are going for higher density. The energy density will be more. Okay. So here, one way is that for doing the simulation, you need the data on 3 directions. So that you can do manually, or theoretically you can calculate, or you can do the simple compression test. Okay, you can do with the compression test in all 3 directions, you can get the curve. Okay. So this is the crushing force versus your crushing distance. So how much load is happening, and how to calculate the SCA. You can see here. You see here, this is for 3 structures. T1 is that I told you, these are the outer casing. So what is that outer casing dimension? So this is I told you, this is completely as rectangular shape, and here one simple corrugation is here, and this is double corrugated is here. That is T3, and for different combination that is T1 H1. So which one is better? Which one is taking large load, crushing force large will be T1 H3. Okay, T1 H3. So that takes large amount of forces. Okay, the amount of force required for a unit deflection will be more in the category of T1. That means when that thin structure is more and you are using larger density. So that is applicable for everywhere. Whatever structure you are taking, the H3 is coming good. Okay, because for unit deflection you need to apply more load. That means what? It absorbs more energy. It absorbs more energy for closing. And see here, this tabular column will give you what is the capacity of this honeycomb structure. You can see. Say for example, in the case of T1 H3, here this is for honeycomb structure only. The honeycomb structure only. So here, how much that will absorb? Specific energy absorption, energy absorbed per kg, you can see here 24.47. So this gives an idea. So this paper we are using for our work. So we are doing some research work. Okay, for that we are using. So the literature gives us some idea about when you are using this kind of material. This is that cell size and all, and it can absorb what? 24.47 kilojoules per kg. Suppose you are giving say 10 kilogram. Okay, you are designing 10 kilogram. It can absorb what? 240 kilojoules. Now you go back to the problem. Now this one, how much energy it has to absorb? The kinetic energy to be absorbed at a higher speed, higher collision speed of 45 km per hour. It is 1000, right? It is 1008. That much amount of energy has to be absorbed. So that means if you are using this cable for that, okay, now this T1 H3, it is 24.47, right? It is 24.47. So how much kg you have to give that buffer or that thing, the energy absorber plate has to be designed for what? It has to be designed for 10 kg it is 240. So 40 kg, so that will give you around 100. Okay, 1000 kilojoules. So if you are using around 50 kg, it will absorb that entire energy that will absorb the entire energy caused by this collision. You have to provide, okay, this, you can have two energy absorbing structures here, each with the 500 kg. Okay, sorry, that you are designing with what? Your every kg is 25. That means we have to give 50 kg. 50 kg will that will absorb 1000 kilojoules. That means you have to use that 25 kg, 2 units of 25 kg. That will absorb what? The entire energy. Okay. Then it will not transmit to what? If you are designing like that, it will not transmit any force to the middle car. It will completely absorb at the front section itself, and it will not transmit anything to the structure. Okay, here this impedance and all not used. Only thing is that we are using this, we are making use of this honeycomb structure and it pressing behavior, it absorbs energy. Okay, So this is one case I would like to, and this will be again, it's a pictorial representation of the energy absorption capacity of that. The another one is that I told this how we can use that foam structures for dynamic response of blast resistance. I told blast resistance in these RB vehicles and all, they are subjected to the hand grenade attack or the floor plate mine blast. So that can be minimized or that can be absorbed by means of layered arrangement of this. Okay. Here you see different combinations are tried. I'll just give you a brief thing so that this paper you can download the paper and you can see if you are interested. The blast response of functionally gradient foam structures. Okay, so now you got this 6 density foams are being tried here. 10%, 12.2, 14.3, 16.2, 18, 19.7. So then F1 is that foam density of 10%, and F6 is the last one, the higher density, low density to higher density. Then they've used that F1 here, F6, and that in the increasing order of density and the decreasing order of density. And here it is, F1 is that the smaller density and F6 is the large density. So they have designed this 6 configurations here. Okay, they've designed with the 6 configurations, and they wanted to study how the energy absorbing behavior happens on. See here, it is a top phase seed where the blast happens. You see here, this is the here it is a blast happened. You can see the pressure is applied here, and this is where that all the layers are sitting. Okay, all the 6 layers are sitting in between the top and bottom plate. Okay, they wanted to find out what is the behavior of this. This is where your impedance comes into play. Okay, now the density is varying and simultaneously Young's model is also varying. So that means every layer will have different impedance. The F1 will have one impedance, F6 will be other, F5 will be something. So in this case, the larger impedance will be happening in the density, higher density, where the Young's model will also be more, density will also be more. So there you will get the larger impedance value. So to understand the behavior of that, so they have fixed this kind of different configurations they wanted to study. So for better understanding, I could not explain all. Let us take only the 2 configurations, configuration 5 and configuration 6. What is that configuration 5? They are increasing order of density. Okay, they are using increasing order of density. Here they are going in this fashion. Okay, it is in this fashion. The density is keep on increasing. Now I wanted to study whether the stress wave is reflected more, and the when it is reflected more, then the last phase seed would be subjected to less deflection compared to the other structures. The configuration 6 is where the first one is larger density. From that it is, so this is decreasing order of density. Okay, now let us compare these two. What is the work of impedance you can analyze here? Now you see here in this, okay, I will just skip those things. I will come to that. Yeah, this is 5th and 6th, right? Yeah. Let us analyze that one. 5th and 6th. Yes, the red one is that 5th one, and the blue is the configuration is 6. Red one is configuration 5, increasing order of density. So it is actually the response is plotted in this way in a dimensionless fashion. It is del by L, and this is something in terms of time. They use another dimensionless quantity, but anyway, it gives the magnitude of that. If it is higher, that means when it is higher and higher, the back wave deflection will be more. They are calculating what? The deflection of the bottom phase seat. That means what? You see in the application side, this is where your blast happens. Okay, this is where your blast happens, and this is where your passengers will be sitting. Okay, or soldiers will be sitting. So I want that minimal deflection at the back end. Okay, and minimum distance deflection at the back end. That means here the blast happens, and this is where the structure will be there. Okay, so here blast happened, this is a structure. So I should get a minimum deflection at the back end. Okay, whatever deflection that has to be absorbed in between structure. So the last one is what the bottom face is. Now, if we go to the curve, the red one, which is corresponding to that configuration 5. So deflection is more there. Compared to that, deflection is less. Compared to that is significantly less in that configuration 6. Okay, that shows that the decreasing order of density, that means the impedance mismatch is continuously designed in such a way that the transmitted wave is less compared to the reflected wave. So more amount of energy, shock wave created, pressure wave created during the blast are deflected back. Okay, so that less amount of energy and stress is propagated to the subsequent layers, and so that we will get a minimum deflection at the last one. So that is what the observation from this. Okay. Okay. So this is what the 2 case studies I wanted to explain. Now I'll just brief about this. The another kind of nature-inspired structure, which is started using this. It is still in the research labs, and maybe another couple of years. So we will find a lot of applications, real-time applications in it. So where again these are used in the shock wave mitigations, and where blast resistant structure, you want to have blast resistant structure or impact resistant structure, we are using this. See, this is bio-inspired, and this is actually any creatures, if you see crabs, lobsters, the mantis slips in the sea, they are taking the prey by hitting it very hard. Okay? Hitting it very hard. By hitting it very hard, they apply a force, very high amount of force. You see, the force they will apply will be around 1500 newtons. You just imagine that. The creature is very small, but the impulse is very high. Very small fraction of second, they apply huge force. And the velocity, the repeated velocity of what? 23 meters per second. So this much amount of force they are applying on the prey so that they catch the prey. Okay. So how do the other structure? No, this is happening at the frontal section, frontal lobe. Whereas the other sections they are relatively soft and they are undisturbed by the impact that is happening on one direction. Okay. So how do they get it? So they get it by a kind of fiber arrangement called helicoidal arrangement or periodical structure. Helicoidal, periodical structure. Both are important. Helicoidal, periodical. What do you mean by helicoidal? This is not a new. Already those who are working with composite may know that in order to get the isotropic property for this sheet metal or this composite layers, what we do, we are changing this fiber orientation from 10 degree, 20 degree, 30 degree, or 40. Normally we will do 45 degree, 90 degree, like that. Okay, so that because the tensile strength will be more in the direction of fiber. The fiber is more stiffer than the matrix material, so you will get more strength in the fiber direction. So to avoid that anisotropic property or orthotropic property, we are going for what? We are going for arranging these materials in a different direction, and so that what we will get? You will get what? The directional property can be minimized, and we will get the uniform property in all sides. Here in the helicoidal thing, what we are doing? We are rotating these fibers for every small angle, maybe 10 degree or 20 degree, like that. And we rotate this till we get completely rotated, that is 360 degree or 180 degree. After that, again, there will be periodically they are arranged. That means one is that helicoidal, that means every 10 degree or 5 degree or 20 degree, these are rotated. Then after reaching it 180 degree, then we stop. Okay, then we are taking another thing. So this is a periodic structure. So these creatures have such periodic structure. Okay, there. So that actually filter the shock wave, shear wave it filters. So it will not carry that the shocks that is created there will not pass on to what? Will not be passing on to the basic thing. Okay. Here it will not pass on. It will just stop here, there itself. Okay. So how do they do it? By means of this chiral structure or this helicoidal structure. Okay. How many layers have to be designed? It depends on what is your theta value, how many number of layers. And actually this is where, this periodic structure. You see every line that is from here to here. This is one period. Then from here another period. Period means that it is rotated completely for that 180 degree or 360. Then next layer has come. So you just look at that. So through this, if this impact happens here, so when it goes inside, this is only a soft layer. As there are two regions, it is hard compared to this, and it is softer. And this is more softer in the third region. So the amount of impact happens is not transmitting to that adjacent region. So it is safer. It is safer. So this is happening in that mantis strip. Okay. So they, I told they are using this huge velocity of 1500 Newton. Okay. So in fact, they are assumed to be acting acceleration of 10,000 Gs. Okay. 1 lakh meters per second square. That is the acceleration that is happening there. 10,000 G. So they are retaining their structure, and that soft elements in that is not get disturbed by that. And this is the newer thing, and this is called as a bio-inspired. So many new architecture and so many new this kind of structures are coming up. You can do a lot of research on it. Now we have a good tool like additive manufacturing. So once you design, you can create this. These are not these are biopolymers only. They are not using any metals at all. So that huge strength they are getting with this kind of small natural fibers, naturally available fiber. They are not using any high strength metal and all. So this we can do with this simple 3D printing. Only thing is that we should have this, we should have design and other things in our hand. Then we have to print it. Okay, this thing is now very easy. Earlier even hand layup and all, it is not possible. This kind of chiral structure, but we can try with whatever additive manufacturing. 3D printing, you can do all those things. Okay, so with this I complete. If you have any question till that point, you can answer. If you have any question, give me answer.
Thank you, sir. Thank you for a nice session. Dear participants, do you have any doubts or clarification? You can ask with expert.
Hello, sir.
Yes.
Sir, good evening, sir. Sir, I
Yeah.
have one doubts. Sir, actually, the honeycomb structure have it's look like a hexagonal.
A little
type.
louder. My audio is not so good. So maybe little louder you may talk.
Yes, sir. So in honeycomb structure,
Yes.
if any one hexagonal passage have some tear or failure in particular place, then in how it will react in remaining places.
Well, Murugan, can you, if you can.
Yes, sir.
Uh,
Sir, the participant he has raised the question of in honeycomb structure, if any defect or failure happened in a particular location,
yes.
how it will reflect in remaining locations?
Yes, yes. So that is there, because when you are fabricating that material, and they are doing that spot welding everywhere. Actually, it is only welding. Through welding only they join this. Initially, they make the corrugated triangular shape, then they join through welding only. So there may be the faults are there, and but in fact, when you compare this, the loading behavior, this faults will not much change the stress strain behavior or energy absorption behavior. Even a small defect there, here and there, will not much vary the stress strain behavior. And there are a lot of work is that the complete defect-free component, the quality control, everything is there. Like any other fabrication work, for honeycomb also, they wanted to fabricate it at the high precision without any defect. But definitely there would be defects will be there, but it will not much change the stress strain behavior. Because normally these structures, suppose if you want to create of 100 mm thickness, the maximum it could go for 20 mm only. So even if defect in one thing, it will not be, that is for universal, that means for the entire thickness. So they are actually joined together. Otherwise what will happen, then the buckling problem and all happen. So they have a different layers. So suppose you want to build it for 100 mm, they will go for 30 mm. So the cause of defect is minimized when you have that folding and sheet metal operation for a small thickness only. There will not much change in the stress strain behavior, so energy absorption behavior will not be much affected because of that. Any other question?
Participants, any other doubts?
Yes.
Yes, sir. I think there is no more clarification. Sir, thank you, sir. Thank you for a very informative
So
session
thanks,
on
I thank
test
Dr. Velmurugan and the other organizers of this program for giving opportunity for this. Thank you very much, sir. Thank you all.
Thank you, sir.
Thank you all.
Thank you, sir. Yes, dear participants, the link for the attendance of third session is shared in the group. So you can give your attendance through that link. We will meet in the next session. Thank you all.